In section 5.5b, we're going to be working on finding all of the roots or zeros or x-intercepts for a polynomial function. So the way we're going to do this is we always want to start out by knowing how many roots there are going to be. And if you remember from previous sections, that is determined by the degree. Whatever the degree of the polynomial function is, that's how many roots there will be. Then the next thing we're going to do is factor out a GCF if possible. If the GCF had a variable in it, set it equal to 0 to find a root. Then we are going to figure out how many positive and negative real roots there might be. And that was related to Descartes' rule of signs. Then we will be listing the possible rational roots, which was done by factors of P over factors of Q. Then we split the list and make things positive or negative, positive or negative, positive or negative, dot, dot, dot. Then we are going to test using synthetic division. So what we'll do there is we will put our possible root in the box for synthetic division, and then we list our row of coefficients, and we go through the process of synthetic division. The remainder ends up in this box over here. This row is the quotient row. And then what we're trying to decide by testing using synthetic division is that if the remainder is equal to 0, then x equals the number that was the possible root is a root, and x minus that number is a factor. So once we get 0 for our remainder, then we are going to rewrite our function as f of x equals x minus that number, this number from up here, that was our possible root, times the quotient that we got as a result in our quotient row. And then we're going to repeat the list test rewrite process using the quotient. So then we will list possible factors, possible roots for the quotient, and then test, and then rewrite. And we do that until the quotient is quadratic, then find the last two roots by factoring or quadratic formula. And then we're going, so the process we're repeating is list, test, rewrite, and then repeat. And then we rewrite one last time so that at the end, our function ends up f of x equals x in each parenthesis, however many times we had our root. So if it was degree 4, we'd have 4 parentheses with x's in them. And with no x squareds, no x cubes. So let's do some examples with all those steps. So example 5, find all roots for the function, then write the function in fully factored form. So we're going to start by deciding how many roots there will be. And we do that by the degree. So I look at the highest degree, and that is 5. So there will be 5 roots. So we can kind of at that point make x equals 5 times. And then when we have this whole list full, then we know we're done. Then the next thing we're going to do is factor out a greatest common factor if possible. So our GCF here of this function, all of the terms have x squared. So I'll write that as x squared times 3x cubed minus 7x squared plus x plus 3 when I take x squared out of each of those terms. Now, since my GCF had a variable in it, I set that equal to 0. So I go x squared equals 0. And then I can break that down further to be x times x equals 0. So I get x equals 0, x equals 0. Or I can think of it like x equals 0 with a multiplicity of 2. But that's actually going to give me 2 roots, x equals 0 twice. So there's 2 of my 5, and I only have 3 left to go. So then I will use Descartes' rule of signs to figure out how many positive and how many negative roots there might be. So positive roots is the number of sign changes in my original function. So I started out positive, I switched to negative, and then I changed to positive again. And so I have 2 sign changes, which means I could have 2 positive real roots or 0 positive real roots. And then my negative real roots, I should have put real in there. My bad. Negative real roots, we do f of negative x. And remember what happens there is that my odd exponents switch their sign. So 3x to the 5th becomes negative 3x to the 5th. My even exponents stay the same, so that will still stay negative 7x to the 4th. Odd exponents switch the sign, minus x cubed. Even exponents stay the same. And then count my sign changes. I start out negative, and I change to positive 1 time, so there will be 1 negative real root. 0, the 2 that I've already found, 0 does not count as positive or negative. So in addition to these 2, there will be 1 that is negative and real, and then there will either be 0 positive ones or 2 positive ones. If there are 0 positive ones, I'll still have to fill in these 2 here, which means that those 2 would have to be complex. So we'll see where we get there. Next step is to list the possible rational roots, and then test with synthetic division, and then go from there. So my list of possible real roots, I'm going to use this function. So it's factors of 3, so 1 and 3, over factors of 3, so 1 and 3. And then remember that I split the list and make everything positive or negative. So 1 gets a turn as the denominator, so that's plus or minus 1 and plus or minus 3. And then 3 gets a turn, so plus or minus 1/3. And then 3/3 would be 1. So I only have 2, 4, 6 possibilities. Then I'm going to test. So I'll put a number in there in the box, and I'll use this row of coefficients. So 3, negative 7, 1, and 3. And sometimes at this point, I go ahead and start using a pencil so I can erase stuff if it doesn't work out. And I'll just kind of systematically go through and start testing things. So if I test 1, then the 3 goes straight down. 3 times 1 is 3. Add these 2 numbers. Negative 7 plus 3 is negative 4. Negative 4 times 1 is negative 4. Add these 2 numbers. Negative 3. Negative 3 times 1 is negative 3. Add these 2 numbers, and I get 0. Oh, wow. It's my lucky day. I got one on the first try. Since that remainder is 0, we are going to rewrite my function as my GCF times x minus my number times my quotient row. So I will take my function, and I'm going to rewrite it. So list test rewrite. So f of x will equal the GCF that I had out front of x squared times x minus the number in the box, so x minus 1, times the quotient row. Now remember the quotient row, the degree goes down by 1, so I had been x cubed, so this will start with x squared, so 3x squared minus 4x minus 3. Now once I get to the point that my quotient is a quadratic, I can either use the quadratic formula or factor. So since this is quadratic, meaning it's got x squared but nothing higher, I will either use quadratic formula or factor. Oh, you know what I forgot to do? I forgot to write this root up there in my list. So x equals 1. So now I have 1, 2, 3. I only need 2 more. And it sounds like I can use quadratic formula, which will give me the other 2 roots. So remember quadratic formula was x equals opposite b plus or minus square root of b squared minus 4ac all over 2a. So quadratic formula, x equals opposite of b, so 4, plus or minus square root of b squared, 16, minus 4 times a, which was 3, times c, which was negative 3, over 2 times a, which was 3. Then I'll simplify my discriminant. So that ends up being 16 plus a number, whatever 4 times 3 times 3, 36. So square root of 52. 52 breaks down 2 times 26, which is 2 times 2 times 13. So square root of 52 would be 2 square roots of 13. So x equals 4 plus or minus 2 square roots of 13 all over 6. And then we got to remember that if I can simplify the number that stands alone, the coefficient of the radical, and the denominator by the same number, I have to do that. Those all divide by 2. So I get x equals 2 plus or minus square root of 13 all over 3. Now those are the last 2 roots. So I get x equals 2 plus the square root of 13 all over 3, and x equals 2 minus the square root of 13 all over 3. And then we're going to rewrite one more time. So we'll have f of x equals, we had our GCF of x squared. We had x minus 1 from before. And then just for simplicity at this point in time, we are going to just write x minus 2 plus square root of 13 all over 3, and x minus 2 minus square root of 13 all over 3. And that will be fully factored form. So our instructions were to find all of the roots for the function, which we did up here. 0, 0, 1, 2 plus square root of 13, 2 minus square root of 13. And then write the function in fully factored form, which is that guy. We have a couple more of these to go through. We've got example 6 and example 7. So example 6, find all of the roots for the function, then write the function in fully factored form. We got the same instructions on this one as we do in our last one. We just have different problems. So finding all of the roots looks like x equals all of our numbers. Well, how many roots will we have? The degree is 4, so we're going to need 4 roots. So we'll have 1, 2, 3, 4. And then writing it in fully factored form is going to look like x minus a number, x minus a number, x minus a number, x minus a number. So we have two kinds of answers. So let's go through our steps. The number of roots we're looking for is 4. So there will be 4 roots when it's all said and done. So I'll give myself 4 spaces to write those answers. And then I'll go through my steps. First thing was, is there a GCF? So I look at all my terms, and there is not. So I can't factor out a GCF. Next thing was to decide how many positive real roots and negative real roots. So positive real roots, we look at the function and count how many sign changes. So we start out positive, we switch to negative, we switch to positive, we switch to negative, and we stay negative. So there are 3 sign changes, which means there might be 3 positive real roots, or there could be 1 positive real root because we subtract 2 from that number. So 3 or 1 positive real roots. And then for negative real roots, we have to know what f of negative x is. And remember, the secret to that is that the positive exponents don't switch and the negative exponents do switch. So rewriting that, x to the 4th stays. Negative 3x cubed switches to positive 3x cubed. 5x squared stays. Negative 27x switches. And the constant term stays. So in f of negative x, it starts out positive and it changes to negative at the very end. So there's going to be 1 negative real root. So either 1 or 3 positive and 1 negative. Then we will start our list test rewrite. So for our list, we need factors of the constant term, which was 36, over factors of the leading coefficient, which was 1. So factors of 36 over factors of 1. Now, when your denominator is factors of 1, there's only one denominator. So it makes it really fast to write your list because it'll just be all the factors of 36 and that's it. So we do plus or minus 1, plus or minus 2, plus or minus 3, 4, 6. Then it's 9 and 12 and 18 and 36. So there's a lot of numbers on this list. Then when we test, we're going to put a number in the box. We're going to make our coefficient row of 1 in front of x to the 4th, negative 3x cubed, 5x squared, negative 27x, and negative 36. And remember, we're trying to choose one that gives us a remainder of 0. So I'm going to start with 1. That worked for me last time. We'll see if it's lucky again. This first number drops down. 1 times 1 is 1. Add these numbers, negative 2. Negative 2 times 1, negative 2. Add these numbers, 3. 3 times 1, 3. Add these numbers, negative 24. Negative 24 times 1 is negative 24. I can tell that's not going to add up to 0, so I'll choose another number. So 1 didn't work. Let's try negative 1. Okay. So 1 goes down. 1 times negative 1 is negative 1. Negative 3 plus negative 1 is negative 4. Negative 4 times negative 1 is 4. Add the numbers, 9. 9 times negative 1, negative 9. Add the numbers, negative 36. Negative 36 times negative 1 is 36. Add the numbers, 0. Yes. So one of my roots is x equals negative 1. I rewrite by turning that root into a factor. So I'll have f of x equals, if x equals -1, then the factor would be x plus 1. And then I use this row here to make the rest of my polynomial. It started degree 4, so this one will start degree 3. So x cubed minus 4x squared plus 9x minus 36. And then I'm going to repeat those steps of list, test, rewrite. So I go list, test, rewrite. But this time when I do the list, I'm using this smaller polynomial, which is actually the same list because my constant term and leading coefficient are the same. So it's still factors of 36 over factors of 1. So my list will still be the same as it was. Now, one thing that I have noticed here is that I found a negative root. And I know there's only one negative real root. So when I go to test, I know that no negative numbers will work. Since I already found the only negative real root, because there was only one. So when I go to test, I'm not going to test any negative numbers. I'm only going to test positive numbers. So I'll put a number in there, and I use this polynomial. So I use the row 1, -4, 9, 36. And I'm only testing positive numbers. So I'll try 2. 1 goes straight down. 1 times 2 is 2. -4 plus 2, -2. Multiply 2 times -2, -4. Add those numbers, 5. 5 times 2, 10. That is not 0. So 2 did not work. Well, we'll try 3. Bring the 1 straight down. 3 times 1 is 3. Add those two numbers, -1. Multiply 3 times -1, -3. Add 6. Multiply 18. That is not 0. So we'll try 4. Bring down the 1. 1 times 4 is 4. Add the numbers 0. 4 times 0 is 0. Add the numbers 9. 9 times 4 is 36. Oops, I wrote that down wrong. Biscuits. That should have been -36. Someone needs to stop me when I do that. Say 1, -4, 9, -36. 36 and -36 does give me 0. So now I can rewrite and I can identify my second root, which was x equals 4. And rewrite f of x equals, keep the x plus 1 from before, x plus 1. And then when you have x equals 4, subtract that 4 over, so your factor becomes x minus 4. And then this row right here, because we started with x cubed, now we start with x squared. So it's x squared plus 0x, which I don't need to write, plus 9. So x squared plus 9. And now we have a quadratic. So we could either factor it or use a quadratic formula. Does not matter to me which way you do it. This happens to be sum of squares if you recognize that from when we were factoring. If you don't, just use quadratic formula. We'd have x equals opposite of b. Well, b is 0, plus or minus square root of b squared, which is also 0, minus 4 times 1 times 9, and then all divided by 2 times 1. So x would equal 0 plus or minus square root of negative 36 over 2. So that's 0 plus or minus 6i over 2, which would be plus or minus 3i. So then my last two roots would be 3i and negative 3i. So there's all of my 4 roots, which was one of my questions, find all the roots. And my other question was write the equation in fully factored form. So we'll do that here. Fully factored form would be f of x equals x plus 1 times x minus 4. And then if I had x equals 3i, subtract that over, so x minus 3i. X equals negative 3i, add that over, so x plus 3i. Now the last problem we're going to work on is kind of a doozy. That's why we're doing it, because it does a weird thing. So when we get to the weird thing, I'll tell you, hey, this is the weird thing. But we're going to start it the same way. So find all of the roots. How many will there be? It's degree 3, so we're looking for 3 roots. And we're going to write the equation in fully factored form. So we'll just put all of our answers together up here today on this problem. Okay, so we're going to start by looking for a GCF. Is there a GCF between all of these terms? No, there is not. So the next thing we're going to do is list the possible, next thing we're going to do is say how many positive real roots and negative real roots. Then we'll list possible roots. So positive real roots will count our sign changes. Start with positive, turn to negative, back to positive, back to negative. So we have 1, 2, 3. So there might be 3 positive real roots, or 2 less than that would be 1 positive real root. Negative real roots, we got to get f of negative x. So the terms that have odd exponents switch their sign. So x cubed would then be negative 12x cubed. The even ones keep their sign, so minus 44x squared. Odd exponent switch the sign, minus 39x. Constant term, keep the sign. So in this, there are no sign changes. All of those terms are negative. So that means there will be 0 negative real roots. So when we go to start testing our numbers, there's going to be no need to test any numbers that are negative because all of our roots will be positive. So that leads us to our next thing, which is to list the possible roots. Possible rational roots. So we want factors of our constant term, which was 10, over factors of our leading coefficient, which was 12. So that's going to be 1, 2, 5, and 10 over 1, 2, 3, 4, 6, and 12. Now we have a lot of denominators that have to take turns when we are creating our list this time. So our possible rational roots is going to be a lengthy list of fractions. So we got, we'll let 1 take the first turn. So we got plus or minus everything over 1. So plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Then we'll let 2 take a turn. So plus or minus 1/2. 2 halves would be 1, plus or minus 5 halves. 10 halves would be 5. Moving on. 3. So plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, plus or minus 10/3. Next one is 4. Plus or minus 1/4. 2/4 would be 1/2. Plus or minus 5/4. 10/4 would be 5/2. 6. Plus or minus 1/6. 2/6 would be 1/3. Plus or minus 5/3. Plus or minus 10/3. And 12. So plus or minus 1/12. 2/12 would be 1/6. Plus or minus 5/12. And then 10/12 would be, ooh, I missed one, 5/6. Hopefully you caught that and got 5/6 back here when we were on 1/6. But that's all of the possible rational roots. So then we will start testing. So we had list, test, rewrite. Okay. So when we test, we're going to use the coefficient row, and we're going to put numbers in the boxes here. So our coefficient row would be 12, negative 44, 39, negative 10. And I'm just going to be real honest with you here. All of the answers are fractions. So I'm just going to kind of, yeah, I'm just going to tell you straight out. It's a fraction. So let's try a couple. There's no negatives, so we'll just work with positives. So let me just show you what happens when we deal with fractions here. We got 1/3. We're going to bring down that 12. 12 times 1/3. If you're not a fraction fan, you can do 12 times 1/3. That's 4. Then add, that's negative 40. Negative 40 times 1/3. That is negative 40/3 plus 39, 77/3. And then we do that times 1/3. Which is 77/9. And when we subtract 10, guess what? We don't get 0. So what you should kind of be watching for is like the first time you don't get a whole number here, you can essentially stop because that's not going to work out to give you a remainder of 0. So let me show you what happens when you do get a remainder of 0 so you can see the difference between something that's not successful and something that is. So we'll do 2/3. So the 12, again, just brings straight down. And then we're going to take 12 times 2/3. So 12 times 2/3. And that's going to give us a whole number of 8. Then we add that to negative 44. We get negative 36. And we're going to multiply that again times 2/3. So times 2/3. That gives us negative 24. Add that to the 39. And that gives us 15. See how nice it is? No fractions. Multiply that by 2/3. That gives us 10. And when we add that, we get 0. So we have found a root. That root is x equals 2/3. So then we're going to rewrite. So our function now is going to be f of x equals, it's x minus the number in the box, so x minus 2/3, and then times the quotient row, which will now be squared because it started out cubed, so this is going to be squared. So 12x squared minus 36x plus 15. Okay, here's where things get weird. I want you to think about regular numbers. So think about if we needed to multiply, like, I don't know, 28 times 5. 28 times 5 is not an easy pair of numbers to multiply, but I could think of 28 differently. I could think of 28, instead of being like 28, I could think of it like 14 times 2 and then times 5. So I took a 2 away from the 28, divided it out, and made it 14 times 2 times 5. And then I can do 2 times 5 here, which makes 10. And then 14 times 10 becomes a nicer number to multiply and make 140. So we're going to kind of think of that principle when we look at this situation. Kind of what I don't like is this denominator of 3. So what I want to do is use a GCF of 3 out of this bunch here. So I'm going to rewrite this as 3 times, I'm just working with this, take that 3 out, so 4x squared minus 12x plus 5. And I'm going to keep this as x minus 2/3 for now. But the way that I knew what number to use was because of that denominator of 3. So I took 3 out of these numbers, just like I did up here, and I'm going to put the 3 into the x minus 2/3. So now I'm going to have f of x equals, I take 3 times x, which is 3x, and then I'm going to do 3 times negative 2/3, which is going to give me negative 2, which is a nice number. So it's going to be 3x minus 2. Now that 3 went into there, so what I have left over here is 4x squared minus 12x plus 5. I know that's weird, but that's what you're going to need to do to be able to make this work. So instead of x minus 2/3, you've got to take a 3 out of what's left over here, put it in to make it 3x minus 2. Then we can go ahead and factor this because it's quadratic. I'm telling us to factor because I happen to know that it factors. So it's 3 terms, so we use AC method. So 4x squared times 5, 20x squared. I need things that multiply to negative 12x. So multiply to give me positive, but add to give me negative means they're both negative. So negative x, negative 20x, negative 2x, negative 10x, negative 4x, negative 5x. It's going to be that one right there. So I will have 4x squared minus 2x minus 10x plus 5. The first group I can take out 2x, so that would be 2x subtract 1. Second group has to match 2x subtract 1. So what would I need to divide negative 10x by to get 2x? That would be negative 5. So it'll factor to 2x minus 1 times 2x minus 5. So then my function becomes f of x equals 3x minus 2 from here. So 3x minus 2. And then that factored to 2x minus 1 times 2x minus 5. So I actually have my factored form before I know my other two roots. So my factored form would be this. I'm going to have to zoom out here. 3x minus 2 times 2x minus 1 times 2x minus 5. And then to get my other two roots, I will set each of these parentheses equal to 0. So I'll go 2x minus 1 equals 0. Add the 1 over, so 2x equals 1. And then when I divide both sides by 2 to solve for x, there's my fraction. X equals 1/2. So my other root is x equals 1/2 for one of them. And then set 2x minus 5 equal to 0. So add 5 over. So we get 2x equals 5. Divide both sides by 2. And there's my fraction. X equals 5/2. So that's my other root. X equals 5/2. So I have 3 roots, 2/3, 1/2, and 5/2. And then my factored form looks nice without fractions in it. And that's what those answers should look like.